The next speaker is Roman Le Goff Latimier, and he's going to talk about Markov switching autoregressive modeling of wind power forecasters. To introduce Roman Le Goff Latimier, he completed his PhD degree in electrical engineering from Université de Paris-Saclay in France in 2016, and is currently a researcher with the Satier laboratory, and he teaches at the École Normale Supérieure in Rennes in France. His interests are into modeling of renewable power sources and their uncertainties, and also into optimal management of power systems under uncertainty. So Roman, the floor is yours.
Thank you, Mr. Chairman, and good morning all. I hope everything is okay and you hear me well and you see the slides. It is my pleasure today to present you this work done in collaboration with Enzo Bouedec and Valérie Monbet. So indeed, planning future operations of a power grid requires many forecasts for all the quantities that cannot be perfectly controlled, like consumption or the production of renewable power plants. And then, of course, all these forecasts happen to have errors, even very small, but it is certain that no forecast can be perfect. And then in real time, it will be necessary to adjust the operations so as to mitigate all these errors. And one could here think about the frequency reserve, for instance. And however, when compensating for an error, it could be great help to know how it will evolve in the very next moments. Indeed, as a system operator, we would not take the same decision knowing that an imbalance would vanish in a few minutes, or if we know that it will persist during several hours. So that is why a modeling of the forecast error would be a precious tool to improve the real-time management of a power system. And in addition, such a model cannot be simply inferred from the model used for the forecast, because the forecast error signal would have very different characteristics, such as a zero mean value or a lesser long-term correlation, for example. So the scope of this contribution will then be to propose a model for wind power forecast errors. So the forecast error is defined as the difference between realization and forecast, normalized by the installed capacity. And to the best of our knowledge, the related literature considered until now autoregressive models. So that is to say that the forecast error at the next time step is described as a linear combination of the past observations plus a Gaussian random variable. However, it can be noticed from the represented sample that the forecast error exhibits very different patterns. So some periods have a very high variability with strong errors, while others display small and highly correlated errors. And this behavior cannot be captured within a single autoregressive model. It would call for using different models for each of these regimes. And it just so happened to be the main feature of Markov switching autoregressive models, which is why they have already been used for wind forecast. And the goal of this contribution is therefore to assess the relevance of a Markov switching autoregressive model to describe the wind power forecast errors. So after a presentation of the model and of the statistical behavior, we will use it within an application problem of an optimal control strategy. So by definition, the Markov switching autoregressive model is based not only on one single autoregressive model, but on several, depending on a latent variable, let's call it pi, the hidden state of the model. And this state is not directly observable, and it is ruled by a Markov chain. So this hidden state can change from a time step to the next one according to transition probabilities, and depending on the current value of the hidden state, the evolution of the time series will be completely different. The model identification is performed iteratively so as to maximize its likelihood using expectation maximization algorithm. And then the probability of belonging to one hidden state or to another can be inferred on the basis of the observations as represented here. So the good news at this point is that such a model succeeds in catching the behavior of a wind power forecast error in a very understandable manner. Indeed, in this example, the hidden state can take 3 different values, and one value, let's call it state 1, has a very high probability when errors are very low with high correlation. Another value of the hidden state, so let's call it state 3, is very likely when a high error with low correlation is observed. And finally, there is an intermediate regime, state 2, which avoids direct transitions between the two previous states. So to illustrate the added value of a Markov switching autoregressive model compared to an autoregressive one, let's use them for scenario generation. So in this sequence, the first two time steps are supposed to be known, and both models are used to generate possible futures, and the real measure is in red. So we here considered a Markov switching autoregressive with 3 possible values for the hidden state and another 2 for the autoregressive part. So let's call it MS3 area 2. So the Markov switching autoregressive model is able to understand that the previous forecast errors were low, and then it uses the adapted correlation and standard deviation so as to generate low amplitude scenarios. And in comparison, on the right side, an autoregressive model will very rapidly reach its steady state, as illustrated by the 90% confidence interval. And doing the same comparison with very high errors, the Markov switching autoregressive model will again adapt its correlation and standard deviation so as to have a much larger confidence interval. To carry on the comparison and the validation of the Markov switching autoregressive model, we now focus on generating artificial data and comparing their features to the original time series. And of course, the goal for artificial data is to be as close as possible to the original ones. So the first feature we consider is the following. For a given threshold value, so illustrated here by the horizontal black line, how many times does it cross the series? And computing this for the original time series gives a yellow profile, and we do the same for artificial data from the autoregressive model in blue and for the Markov switching autoregressive in red. So basically, the series crosses more often near 0 values, and the autoregressive model exhibits a symmetric Gaussian pattern. However, the original series shows a specific shape, which in addition is non-precisely symmetric, and this very particular shape is very well reproduced by a Markov switching autoregressive. A second feature we consider is after upgoing a threshold, how long does the series stay above? So that is to say, what is the mean duration of the gray zones in this illustration? So if a threshold is very low, the series will spend a very long time above it, whereas if it is very high, the series will only stay above during a few time steps. And here again, data generated by Markov switching autoregressive model is much closer to the original than the simple autoregressive model. And its performance is, let's say, close to perfection for small values, but of course the tails of this feature are much more difficult to capture, as pointed out by the previous presentation. However, this extremely high and low value are quite rare, and the differences are here magnified by the logarithmic scale. So the statistical fidelity to the original time series is significantly improved in comparison with an autoregressive model, and it even makes possible to imagine a future integration within artificial weather data generators. So let's say that the generated data could be provided along with their associated forecast error. So to go beyond this statistical validation, the model is now used within an application problem. So it is chosen as simple as possible, but still representative, to make easier the result interpretation. So we considered a wind farm associated to a stationary storage, and this virtual power plant is supposed to be subjected to a production commitment. So the forecast is used to decide the commitment profile, and then the storage is managed to mitigate the errors in real time. The optimal control problem of the storage is then to minimize the cost associated to the commitment gap, chosen as a quadratic function, plus quadratic losses. And those quantities are to be minimized in expectancy over an infinite optimization horizon. And the forecast error model will be used in the expectancy computation. The related constraints are the limits on the storage power, the limits on the state of energy of the storage, and the dynamic equation of the storage. And so the resolution of this problem is carried out using stochastic dynamic programming. So the Bellman equation allows to compute an optimal strategy which describes the optimal decision for any configuration of the system. So here the state vector of the system is the storage state of energy in the x-axis and the current forecast error value in the y-axis. But this strategy also depends on the current state of the Markov switching autoregressive model. So indeed, if the correlation is low, the optimal control will not try to anticipate the future, and vice versa for a high correlation. So that is why there is such a strategy for any possible hidden state. And basically, this strategy sets the storage power so as to compensate for the forecast error as long as the ISO power lines are horizontal. And when the storage is full or empty, the ISO powers become vertical because the storage cannot provide anymore. And the correlation coefficient make possible to optimally set the anticipation of the saturation. And for comparison purpose, this resolution is carried out for both autoregressive models and Markov switching autoregressive with various orders. However, there is still one obstacle to assess the added value of the forecast error model. Indeed, the overall performance of the storage does not only depend on the model, but also on the storage size itself, because a big enough storage does not require any advanced management, and similarly, a too small storage will be immediately saturated, whatever the control strategy. So that is why we chose a co-optimization approach of the sizing and the control. So first, here is the evolution of the cost associated to the management problem depending on the size of the storage. And for this blue curve, the control strategy is myopic, so the storage perfectly compensates the error until saturation without any anticipation. And of course, the cost decreases with the size of the storage. And then we look at the enhancement that a forecast error model can bring compared to this myopic baseline. And using a model as simple as an autoregressive of first order already brings up to 57% of cost reduction. And here again, this depends on the storage size, because the larger the storage, the better the latitude for an intelligent control strategy. And what could happen with the introduction of the Markov switching property? So here is the same improvement curve, but with a control based on an MS2 AR1, then an MS3 and an MS4. So the Markov switching property does bring a further improvement, but it seems to reach a limit as the improvement is smaller with the order. And in a second time, what could happen if the autoregressive order is increased? So here are the results for a second order autoregressive model. So we can notice that for a large storage, it outperforms any Markov switching. But when the storage is small, it is barely better than an AR1. And adding an MS3 AR2 leads to the conclusion that for a large storage, the performance hierarchy is the following. Down there is AR1, then all decline Markov switching models. Second order autoregressive hits a ceiling, and then again Markov switching goes higher. So for a large storage, the impact of the autoregressive order is the most important, more important than the Markov chain order. However, for smaller storage, AR1 and AR2 are below any Markov switching model, and therefore the impact of the Markov chain order is the most important. And this is very relevant for a small storage, which is unable to mitigate long errors correlated over several time steps. So therefore, there is not a unique optimal choice for the forecast error model, as it depends on the size of the storage unit. So as a conclusion, I remind that we here proposed a Markov switching autoregressive model to catch up the various dynamics of the wind power forecast errors, and the artificial data generated by this model are statistically very close to the original theory. And in addition, using such a model for the management of a storage unit made possible to significantly improve the error mitigation. Many features could still be added within this model to make it even more faithful. So I will mention the possibility of taking into account meteorological covariables, such as the temperature or humidity. And in particular, the forecast itself could be a very interesting covariable. So the consequences would be that the transition probability would not be a constant value anymore, but a function depending on those covariables, and the model would then be using non-homogeneous transition probabilities. Another improvement hint would be a coupling with other quantities being forecasted, so it could exhibit underlying correlations between, for instance, energy price, consumption, or solar production. And finally, a last perspective could be to transpose this model to several wind farms so as to take geographical effects into account. So thank you for your attention, and I will do my best to answer any question you may have.
Okay. Thanks you very much, Roman. Thanks for the timekeeping and for a nice presentation. It seems you have a few issues with your connection. Actually, the sound was a bit tricky sometimes.
I apologize.
I mean, no problem. Or it's on my side maybe. But there are two questions in the Q&A that I think are very interesting to start with. I hope you can see the Q&A also. The first one is from.
Since I have shared the screen, and since then I don't see the.
Okay, then I'm going to read the question. There's the first question by Loic. Do you know which method is used for the forecast that yields your forecast error time series, or maybe what do you expect in general? And would it be possible that your method performs differently on time series obtained with a different forecasting method?
Yeah, this is a crucial question actually, and thank you for asking that. Because for that first study, we chose to rely on an open source time series provided by the Bonneville Power Administration, and it is an aggregated time series. So the forecast is aggregated for several wind farms in a wide area. So I can't answer precisely the question. I'm sorry for that. Because I guess that they have made a lot of expertise in order to have it as good as possible. But I guess, as it is a day-ahead forecast, so I guess that the answer would be a numerical weather forecast. But we chose to stick to this day-ahead line because, as the question suggests, if we go deeper and, for instance, consider some forecast for intraday or just a few hours ahead, then we will have much more difficulties to handle the fact that the forecast is released, and then for the next few hours you have to cope with this forecast, even if it happens to have errors, and the errors are getting larger and larger. And then suddenly a new forecast is released, and then the error goes smaller with a kind of irregularity in the time series.
Okay, thank you for that. There was another question from Zhao Yuan, which is about a certain slide. So you might want to share your screen again. In slide 5, in terms of how long the values stay above the threshold values, it seems that your AR2 method is more close to the original data than the MS3 AR2 method for high threshold values. Why?
Excuse me, I was I was thinking about the screen sharing, so I hope you can see it again.
Yes, you're starting to share your screen. So in slide 5, in terms of how long the values stay above the threshold values, yes, it seems that the AR2 method is closer to the original data than the MS3 AR2 method for high threshold values.
Sorry, but I don't think so, because the red curve and the yellow curve are exactly one above another for the small values of the threshold values.
Yes, so you think it was maybe more of an optical effect? There's no clear difference. Yeah. Okay. All right. A very quick question, actually, which is, I know we have Patrick who asked a question also, which I think is a very good one. How do we select the number of states and the degree of the autoregressive model? Is this just trial and error or something like a AIC, BIC?
Actually, thank you for the question. If you don't mind, I will switch to a backup slide, because I was
we don't have much time for that
to discuss this question in the presentation. And here is the big criteria for several models. So can you see it well enough?
Yeah.
Okay, thank you. And so we tested up to the third order autoregressive and up to the four values for the hidden state. And on the sole analysis of the big criterion, we had no clear choice on how to decide the model. So, which is why we concluded that it wasn't a sufficient point of view, of a sufficient perspective to assess the value of such a model. And afterwards, we switched to the application problem perspective in order to assess what could be the right decision to do, the right decision to make for such a model.
Okay, so thank you very much. I think we need to move on. So thanks a lot for a very good presentation and a good discussion with the questions. Another virtual approach, Roman.